And the effect of that is, if that's a positive bias, they'll say everything's running from the 5 volt supply for shown in this example. You get 5 volts in there. At the output of the first inverter, because that switch has been switched on, that connects the output terminal to your 0 volts rail. So you get 5 volts out, inverts, 0 volts in. But 5 volts in gives you 0 volts out, and conversely 0 volts in gives you 5 volts out. And in logic terms, you've taken your 1 and you've inverted it to a 0. Put 2 of them in series and arrange some feedback. If you have logic 1 here, or 5 volts here, 0 volts here, that therefore, because it's another inverter, gives you 5 volts there. Feed that back to the input. Then when you disconnect this from any external circuit, it remembers the state that it was left in.
Is it worth mentioning that the power required to store the bits comes from the input, so you don't need to keep it powered?
That works in the flash device, but it doesn't work in this device. With this device, as soon as you turn that power rail off, everything disappears. Whereas the key thing about this is, if you say you have 2 switches here, or a single switch here to switch between, say, 5 volt or 0 volt. As soon as that switches, if that's a push button, you push it to 5 volt, that would remember 5 volt until you then next gave it a different input. Let me explain the key principle of how this display works. Any ideas? I think you probably did it again. You've done something similar in the block 2 TMA, so probably don't need to spend too long on it. But
is it when there's no voltage applied,
right.
the liquid crystal flips the light 90 degrees,
Yeah.
so it goes all the way through. But when you do apply a voltage, it destroys the liquid crystal.
Basically,
ability
yeah.
to
It's
twist
sort of,
it.
basically, yes. Okay. Something I haven't seen in the 2MA out questions yet, but will probably feature, is the understanding the manufacturing process for practical CMOS devices. This is all in the techniques book in block 2. So basically, you need to be able to talk about the process steps, what limits how small you can make CMOS, although I think technology's moved on a little bit since the book was printed, and also talk a little bit about the materials used in building a CMOS device, or an array of CMOS devices. CMOS, you might be asked what it stands for, but I'm not sure. It's a combination of N-channel and P-channel switches. Use something called shallow trench isolation to divide your substrate up into those P and N-channel switches. And by using complementary pairs of switches in the same device, you minimise the power consumption of your circuit. One of the things to do with scaling this CMOS down to smaller and smaller transistors is, if you reduce the dimensions, you need a smaller area between the gate. And also the main capacitance of the thickness of the oxide layer has been reduced. There's a limit to how thin you can make this, and it still functions as an insulator. And then we go to talk a little bit about possible alternative dielectrics to silicon dioxide. Okay. Right. Can anyone remember the main process steps in making a CMOS circuit?
Starts off with lightly doped.
Pardon?
Start off with lightly doped.
Yeah, start with a lightly doped substrate.
You etch in the shallow trench.
Yeah.
Do you etch the shape and then you fill it with the.
Yeah.
Then you put the oxide layer on it.
First, you need to put your P and N type layers in.
Then you mask it.
Areas in.
Yeah.
Bombard it and then take it off, mask the others. And
Yeah. So basically, as you said, trench isolation, then you dope the wells, then you grow the gate oxide, pattern the gates, dope the contacts. That's the area that you saw either side of the channel in the previous the earlier slide. Encasing your gates in oxide, spatial deposition, making the contacts, basically you convert the surface of the contact to this silicide thing so that you can make a metal contact onto it without it acting as a shocky diode. And then you add your wiring, which could be aluminium or tungsten. Further gap filling and then polishing it so you can add further, more interconnect layers on if they're needed. That is basically block 2. Short and short.
Do you know that last bit you covered there? There's a question, isn't there? It's sort of a part B question.
Yeah, that's why it's
Are we just basically going to reproduce
that
that
sort
and
of
expand
argument.
on that? Yeah.
Yeah.
How much detail would you need to go into? I had a go at doing that question. I think covered about 4 or 5 sides of A4.
Probably 4 or 5 is too many.
Yeah.
I think.
Basically, because the whole technique.
I work on the basis of roughly 1 mark per thing that you're being asked to produce.
Right.
So if you've got 8 marks, then you can sort of think, okay, you're looking for sort of either 8 statements or 8 explanations, 4 statements, 4 explanations, that sort of level of,
Going by your
roughly.
descriptions,
Yeah.
I'm thinking you've always been very tough with marking my TMAs.
It probably wouldn't be as quite generous.
Then I'm just stupid.
Look at the feedback and see, hopefully he's given you some clues as to what else he was expecting. Okay, any questions on block 2 before we have lunch? Have you all brought lunch with you?
Yes.
If not, I think there are vending machines downstairs and there's a Costa half a mile up the road.
So shall we start again at 1:20?
So ready some customers?
How did you get here?
Taxi.
is it all on the roundabout?
It's the one on the roundabout up.
So back towards town.
Back towards town.
Yeah.
It's just at, I think, just before 5 Ways.
Okay.
It's the